Implementing secure cryptographic algorithms is hard. The code must not only be functionally correct, memory safe, and efficient, it must also avoid revealing secrets indirectly through side channels like control flow, memory access patterns, and execution time. Programs that have these properties are said to be constant time. Lots of recent work has focused on helping programmers write constant time code through type system, program transformations, and automate the verification of constant time implementations. Unfortunately, these efforts are crippled by speculative execution. Even if programs control secrets closely through bounds checks, the processor can simply ignore them when executing speculatively. An attacker can exploit this behavior by leaking secrets to the cache, where they can be recovered through cache timing measurements. In principle, programmers can insert fences to stop speculation and so avoid speculative leaks. In practice, however, fences pose a big problem. Programmers can restore security by conservatively inserting fences after every load. However, this will cause a huge performance overhead. Alternatively, they can rely on heuristics to insert fences in their code, but give up all guarantees about the absence of side channels. This is because even missing a single fence can expose the whole process memory to the attacker. This risk is so serious that browsers like Chrome and Firefox isolate secrets from untrusted code in a different process just to avoid the risk altogether. In this work, we propose a solution to improve the situation. Blade is a new, fully automatic approach to provably and efficiently eliminate speculative leaks from constant-time cryptographic code. The key inside of Blade is that to prevent speculative leaks, we don't need to stop all speculation like memory fences do. Instead, we only need to stop speculation along specific data paths. In particular, we only need to cut the data flow from source expressions that speculatively read secrets to sync expressions which leak them through the cache. To do that, we propose and formalize the semantics of a new abstract primitive called protect. Unlike regular fences, protect stops speculation only for a given variable. For example, this protect statement ensures that the value of e is assigned to x only after e has assumed its stable, non-speculative value. Craig will tell us later how we implement protect. For now, you can think of it as a fine-grained fence. Blade inserts protect statements to eliminate speculative leaks. First, Blade identifies source and sink expressions in a program. Then, it detects data flows from sources to sinks. And lastly, it inserts protect statements to cut the source to sink data flows. The program on the right is now secure because the protect statement prevents any secret introduced by the source from reaching the sink. In order to detect speculative leaks, Blade tracks speculative data flows by means of a static type system. The type system conservatively approximates the dynamic semantics of speculation using two types, transient and stable. Expressions are typed either transient if they can contain transient secrets, or stable if they cannot. The type system performs static taint tracking and treats transient expressions as tainted. The typing judgment for expressions simply propagates the transient taint, and the judgment for comments restricts the use of transient data to avoid leaks. Intuitively, programs that are well typed according to this type system are free of speculative leaks. To avoid secret-dependent memory accesses, the rule for reading arrays requires the array and the index to be typed stable. Since reading an array out of bounds can transiently introduce secrets in a program, the rule types the result as transient. Similarly, to avoid secret-dependent branches, the type system does not allow branching on transient data. Without protect statements, existing programs are likely insecure under speculation and will be rejected by our type system. Therefore, we have studied an algorithm that finds potential speculative leaks and synthesizes a minimal number of protect statements to ensure that programs are speculatively constant time. Let me show you how the algorithm works with an example. This program reads two values from array A, adds them up, and indexes array B with the result. Like the Spectre gadget from before, this program contains a speculative execution vulnerability and is ill-typed because Z is typed transient instead of stable. To repair the program, we first build its def-use graph. The directed edges between the nodes of the graph capture the data dependencies between the variables and the expressions of the program. For example, the edge from x to x plus y indicates that x is used to compute x plus y. To track how transient values propagate in the def-use graph, we extend the graph with two special nodes, node T and node S. Node T represents the source of transient values. Therefore, we connect it to all the nodes containing expressions that explicitly read memory and thus introduce transient values in the program. Similarly, node S represents the sink of stable values. This node draws all the values of the program that must be stable to avoid transient execution attacks. Therefore, we connect all expressions used as indices in the program to this node. The fact that the graph contains a path from T to S indicates that the program may be leaky. Intuitively, this is because transient data flows through data dependencies into what should be a stable index expression. To secure the program, we need to cut the data flow between T and S by inserting protect statements. This problem is equivalent to the problem of finding a cut set. A cut set is a set of variables such that removing these variables from the graph eliminates all paths from T to S. To repair the program, we only need to insert a protect statement for each variable in the cut set. The program on the right is now secure. However, the repaired program contains more protect statements than strictly needed. This is because the cut on the left is suboptimal. In contrast, the cut on the right is minimal because it requires a single protect for variable z. A minimal cut is preferable because it requires as few protect as needed, and therefore it allows for more speculation safely. Luckily, the problem of finding a minimal cut is a classic graph problem called max flow min cut, for which efficient polynomial time algorithms exist. One of the goals of Blade is to enable source-level reasoning about the absence of speculative leaks. In order to prove our type system sound, we need high-level reasoning principles. However, the effects of speculation manifest only at the very low machine level. Clearly, there is a mismatch between the two. We reconcile this tension by giving the first source-level semantics model of speculation. Unlike previous semantics of speculative execution, our processor abstract machine does not operate directly on compiled assembly programs. Instead, our processor translates high-level commands into low-level instructions just in time. Individual commands are translated directly, while more complex commands are translated in multiple steps. To do that, the processor relies on two data structures, a stack of partially flattened commands and a list of fetched instructions called reorder buffer. We model a simple processor pipeline consisting of three stages: fetch, execute, and retire. We don't fix the order in which instructions and their individual stages are executed, and we don't model the branch predictor. Instead, we let the attacker explicitly control the processor through a set of directives. For example, by supplying directive fetch true, the attacker instructs the processor to predict outcome true for the next if-then-else command. In response to that, the processor replaces the if-then-else on top of the stack with the then branch. Furthermore, to record the fact that from now on this execution is speculative, the processor inserts in the reorder buffer a pending guard instruction. This instruction contains the condition and its predicted outcome. Importantly, the guard instruction also contains the else branch together with a copy of the current stack. This stack allows the processor to perform a rollback in case of misprediction. We prove three formal results about our JIT semantics and Blade. First, consistency ensures that programs running on our processor produce the same results with respect to the memory store and variables as if their commands were executed in order and without speculation. Second, we prove that our repair algorithm is correct and synthesizes well-typed programs. Lastly, we connect the type system to our JIT semantics by proving that well-typed constant time programs are also speculative constant time. This result extends the sequential constant time guarantees of verified cryptographic code to our speculative execution model. Craig will now tell us more about the implementation and the evaluation of Blade.
All right, thanks. As Marco said, I'll be talking about the implementation and evaluation of our tool Blade. So the first question is really, how do we implement this protect primitive that we've been talking about over the past several slides? And ideally, we would implement protect in hardware. With a dedicated hardware primitive, we could targetedly restrict speculation only along a particular data flow path, while allowing all other speculation to continue. This would give us maximal performance because we'd be allowing as much speculation as is safe. At the same time, we'd have minimal instruction overhead because protect would be just a single instruction. And there are some previous work on hardware schemes that suggest how we could implement protect in hardware. But in the meantime, it would be valuable to have an implementation of protect in software. That way, we could secure programs that are running on today's hardware. So we experimented with two different software implementations of protect. On the one hand, we have fences. Fences are certainly secure, but they can be detrimental to performance because they actually restrict more speculation than is necessary. They cut off all speculation at a particular program point rather than only along a particular data flow path. We also experimented with using speculative load hardening, or SLH, to implement protect. And I will briefly explain how SLH works. In order to use SLH to protect this array read here, A sub E, we replace it with this 3 instruction sequence. And what these instructions essentially do is they conditionally mask the address to 0 based on the result of a bounds check. The important thing to notice about this code is that we use a conditional move, or cmove, instruction on x86, which ensures that we can't misspeculate the value of the mask. So now that we've talked about how we implement the protect primitive, let's talk about the rest of the implementation of Blade. We implemented Blade as a compilation pass in the Cranelift code generator. Cranelift compiles WebAssembly bytecode to x86 machine code. So here's a typical compilation pipeline that uses WebAssembly. You can see that we take source code, compile that to WebAssembly bytecode, and then Cranelift is responsible for turning that WebAssembly bytecode into x86 machine code. And it's there that we insert the Blade compilation pass. As another note, although we implemented Blade for Cranelift and WebAssembly, nothing about it is inherently specific to Cranelift or to WebAssembly, and we could easily imagine implementing Blade in Clang or really any other compiler. So we evaluated Blade on a data set of verified constant time cryptographic code. All of the code in our evaluation was verified to be constant time in the sequential sense, meaning that it doesn't leak secrets when considering only sequential execution. However, our evaluation shows that in many cases, this code still requires additional protections in order to be secure from speculative attacks like Spectre. We took cryptographic code from two different sources for our evaluation. First, we used some verified cryptographic primitives from the CT-WASM project. And second, we also took some automatically generated verified WASM code from the Hackle-Star project. Our evaluation shows that Blade inserts an order of magnitude fewer protections, that is, fences or SLH masks, than our baseline scheme. And our baseline scheme just inserts a protect for all loads that have non-constant addresses. This is very similar to what's done today in Clang when you use its speculative load hardening pass. We also implemented or measured the runtime performance overhead of Blade. And we found that for Spectre v1 protection, it imposes only about 1.7% overhead on average when using SLH, or about 5% when using fences. Blade can also protect from both Spectre v1 and v1.1, and this still results in modest overheads between about 15% and 27% on average.
In this video, we have presented Blade, a new fully automatic approach to provably and efficiently eliminate speculative leaks in unannotated cryptographic code. Blade statically detects data flows from transient sources to stable sinks and synthesizes a minimum number of fences and masks to eliminate potential leaks. We have implemented Blade in the Cranelift WebAssembly compiler and evaluated our approach by repairing several verified, yet vulnerable, WebAssembly implementation of cryptographic primitives. Thank you for watching.